All right, so now that we've got our equation, right, for potential energy, our equation is potential energy equals mass times acceleration of gravity times the height of the object. We're able to start using it in some calculations. So I've got a scenario for us here. We've got a 10.2 kilogram block of ice. So maybe you're an ice sculptor and you want to move this ice from the ground to a table that's 2 meters above the ground so you don't have to be bending over as you're sculpting your ice sculpture. Okay, and we want to know what is the change in your ice block's potential energy through this move. So first we're going to take out our numbers. So you've got your 10.2 kilogram block of ice. Our ice is not changing masses from the ground to the table, so that number is going to be for both situations. It is going to end up 2 meters above the ground, and it is starting from the ground, which we're going to know is a height of 0. Because we get to assign where 0 is, and I always suggest to put 0 at the lowest point that your block or your object is at. And we want to know what is the change in potential energy. Okay, so I suggest to first draw out what's happening. Okay, so we've got the ground, and I like to say that the ground is going to be height equals 0 meters. And before, we've got this ice block chilling on the ground, and then afterwards, we've got a 2 meter tall table and our ice block is chilling on top of that table. So that's our scenario. So now we're going to go ahead and calculate our potential energy before and after the block is moved. So before the block is moved, we're going to use that equation, mass times gravity times height. Mass of our block, 10.2 kilograms. That's not going to change. Gravity is on Earth, so 9.8 meters per second squared, and then we've got a height of 0 meters. All right, anything that is multiplied by 0 is going to be 0, so we know we're going to end up with potential energy of 0, but we're going to figure out our units here. So we got kilograms times meters per second squared times meters. And if we go ahead and simplify this, now we've got kilograms times meters squared over seconds squared. And physicists said this whole kilograms times meters squared over seconds squared was just a mouthful, and so they simplified that to be something called joules. So J stands for joules, and joules is the scientific unit of energy. So a joule is our scientific unit of energy. All right, so that is the left side. Then we're going to go ahead and we are going to solve for the right side of this problem. So after we lift the block up, we're going to use that same potential energy equation, right? Our mass of our block is still going to be 10.2 kilograms, not going to change. Gravity also, we're still on Earth, so that's not going to change. And then now we've got our new height of our block. We've put it on a table that is 2 meters above the ground. All right, so then we go ahead and we simplify this. We say 10.2 times 9.8 gives us a potential energy equals 99.96. Let's carry our units down, kilograms times meters over seconds squared times 2 meters. And so we'll multiply that by 2, and we will end up with a potential energy of about 199.92. And we already figured out that our units can be joules. So that's the potential energy after we lift our block up. Now we go back up to our problem, and our problem says, what is the change in your ice block's potential energy? So it's all good and fine that we found energy before and after, but we want to know about the change, okay? And so our change in potential energy is going to be equal to the potential energy at the end of the move minus the potential energy at the beginning of the move. So I'm going to look back at my potential energies. I'm looking for my final potential energy, and that was after we put the block on the 2 meter tall table, and so that's 199.92. I'm going to go ahead and round this to 200 joules. And then we want to subtract our initial potential energy, which is when the block was on the ground at a height of 0. And so that's going to be 0 joules. And so 200 minus 0, our change in potential energy is 200 joules. Do you see how making the ground as height 0 really helped me simplify that math, since I only really had to solve for one side? All right, so that's how we're going to be using this equation